And the last talk of the day is the first lecture of Yuval, Filmus, on structure theorems in Boolean Function Analysis.
Boolean Function Analysis.
Yeah, I'm sorry. FA always. You had Harmonic on your title. It was
right. Yeah, so we're going to start by telling you what we're going to do today, and then we'll start with maybe some philosophy. So today we're going to start with an application, which is kind quantitative arrow theorem, and then we're going to discuss the FKN theorem. Okay, so that's the initial goal for today, and if for some reason I'm going too fast, then we'll get even further. Yeah, so what is Boolean Function Analysis about? So now I'm already told you all about it, but still, just because maybe somebody is not watching the talk straight, so Boolean Function Analysis is about functions on the Boolean cube. Okay, so we're discussing functions like this. Often the functions of themselves will also be Boolean, but not always. Okay? So we have our Fourier transform. It's the same thing all along. I mean, there's only one notion of Fourier transform, but just for completeness, we use a different normalization. So for us, Fourier expansion looks like this. Okay, so this is the Fourier basis, XS, now I use Ries, it's the same thing. And these guys, they form an orthonormal basis with respect to the following inner product. So, okay, so this is the expectation over all x with respect to the uniform measure for now of f times d. Okay, so you can see one difference between my talk and Alex's talk. Maybe somebody can spot a difference, crucial difference.
Difference with what?
With what we saw with the previous two talks.
Normalization? No?
Right, this is one difference, good. So it's like these children's books where you spot the difference. What's the second difference?
Real value.
Real value, excellent. Yeah. So I don't care about the complex numbers, okay? Everything works. It's probably not true, but probably you can make things work if you need for some reason to work over the complex numbers, but we would not need to because in TCS where I come from, or in combinatorics, our application is eventually to Boolean functions, and Boolean functions are not complex. I mean, in a sense, they could be complex, but different terms. Okay, so without further ado, this field of Boolean function analysis, it gets inspiration from several different areas of math. Some examples, social choice theory, where some of the terminology comes from, extremal combinatorics, random graph theory, hardness of approximation. This is some part of complexity theory, which is a part of theoretical computer science, and so on and so forth.
Originated from, or at least some of it, from cryptography.
Okay, what?
Binary and linear.
Collective coin flipping?
Yes.
Okay, so even cryptography also makes an appearance in submodular functions, which is a previous workshop I've attended here at the Hausdorff Institute. So all sorts of fun connections, also in circuit complexity, like learning, this is a connection to learning bounded depth circuits. So today we're going to see an application from social choice theory, and it's going to lead naturally to this FKN theorem, which otherwise you could say you just made up some question for you to solve. Okay, so there is like two ways to go around studying this area. One option is like what we're going to see here. We start with a problem in some other area, and it naturally leads you to some question, which you then solve. Okay, this is also what Noam will talk about. The other approach is what I do. You start with some known theorem, and then you prove a similar theorem. And your similar theorem might or might not be interesting, but it's up to some kind of an aesthetic decision. Whereas if there's an application, then you know that you're proving something which is relevant. Okay, but since we're mathematicians, then we don't care about relevance that much. Okay, so now we're going to talk about the work of a Nobel laureate named Kenneth Arrow. So you know that it's something very. I'm not sure he got the Nobel for this. Maybe.
I think he did get the Nobel for that, except it's not the real Nobel, it's the economics Nobel.
Right. Okay, so
It's different prizes.
different committees. It's a fake, right? It's fake in a sense. Public imagination. Yeah, so it's on the topic of elections, which for the Americans, it's a timely topic. So there are elections between three candidates, A, B, and C. Okay, and it's a ranked ballot, which is something that I think happens in some countries, not in the US, but in some countries. So every voter has to rank the three candidates. Yeah, like maybe this is the ranking of one candidate, and this is the ranking of some other candidate, and this is the ranking of another voter. Yeah. So these are three voters, and these are their rankings. And we want to aggregate all of these votes to a single preference. Okay, and we are looking for an order on all the candidates. There's a different theorem if you just want a winner, but we want to rank all the candidates. Okay, you can ask Professor Ken why he was interested in this question, but that was what he was interested in. And he was looking at the following kind of approach. So let's say that you forget about candidate C and you're only interested in the relative order of A and B. So you should be able to determine the relative order of A and B by just forgetting about C also in the votes. Okay, so if C was absent from everybody's mind, like we just erase C from the universe, then you should still be able to determine the relative order of A and B. And this is known as the independence of irrelevant alternatives. Okay, so the kind of aggregation function that we're going to consider, it looks at every pair of candidates and only at their relative orderings, and it spits out an answer. Okay, and you can see that this is a Boolean function. You can think of it as a function from -1, 1 to the n to -1, 1, where the -1s and 1s are the which of two candidates was preferred by each voter, and then it spits out the answer. Which of these two candidates wins in this pairwise ranking. Okay, so one function to try is the majority function, right? So in the US, it's not exactly majority, but still, majority is the first thing to try. So let's see. So a majority of candidates prefer A to B, and also a majority prefer B to C, and a majority prefers C to A. Okay, but that's a problem. Yeah, so you cannot, there's no ranking where A is better than B, better than C, better than A. Okay, so majority doesn't work. So what Arrow asked me,
This is Condorcet's paradox. Condorcet was interested in that.
he's a Condorcet. Yeah, and he ended up his life, I think, in the guillotine.
Yes. Of course.
Yeah, like all initial people in the revolution, they eventually.
I think it was 30 years ago.
Oh, really?
I think it was 1760 something.
Well, when he did this, but not when he was beheaded.
No, we
can do it
when
later.
Yeah, of course. He was beheaded later.
Anyway, so Arrow asked himself, okay, so which social choice functions do work? Okay, so we're going to look at a particular version of the question where the ranking function used for every two candidates is the same. Okay, we can also do like the more general case, but it would just be more technical details. So we just consider this case. So for which, rather, which social choice functions f from -1 to the n to -1 are, I don't remember which term they usually use, but we'll call it eligible here. It just means that when you do this, then you always get an actual ordering. Okay? And these functions are also going to be odd. Okay, so f of minus x is going to be equal to minus f of x. And this is because if I switch the order of two candidates, then I should still be using the same function f. Okay, this is just for simplification. I mean, we can solve it even without these extra additional assumptions. Okay, so I'm not going to tell you the answer. It's going to see the answer in a bit, and then you will see what you need to do to get a Nobel Prize. You can solve this problem combinatorially using some sort of induction. It's not a lot of fun, but it's doable. But we're going to use Fourier analysis. Okay, we're going to follow the footsteps of Yuval. Okay, so yeah, let's see how you would encode this thing as a triplet of Boolean variables. So let's see the ranking A greater than B greater than C. Okay, so there are three items in the agenda, as they like to call it. Is A better than B? Is B better than C? Is C preferred over A? Okay, and let's say I put 1 if the answer is yes, and -1 if it's no, although usually it's the opposite. It makes no difference. So in this case, it's 1, 1, -1. Okay, so there are 8 possible options for 3 bits, but only 6 possible options for permutations on S3. So there are 2 options which need to be ruled out. So which ones? 1 after 1? 1, 1, 1, and -1, -1, -1. Yeah, so we say that this triplet, it satisfies the predicate not all equal on 3 bits. Okay? And if I have 3 bits, x, y, and z, then you can check that they satisfy this predicate if you have this inequality, this equation. So the sum is equal to -1. Okay? So now suppose that f from -1, 1 to the n to -1, 1 is an odd function such that for all x, y, and z in -1, 1 to the n, we have f of x, f of y plus f of x, f of z plus f of y, f of z is equal to -1. Okay, and we want to find out what f is. Okay, so what we do now is what they really like doing in social choice theory. It's called the impartial culture assumption. So let's assume that the votes are random. Yeah, this makes sense to people doing social choice theory. I never understood why. Really. Yeah. But that's what they're interested in because that's what they know how to analyze, and that's what's mathematically interesting. Like, if the vote is skewed, then whatever you do will be skewed and just not interesting. Okay? But in our case, it doesn't matter because we can choose whichever distribution we want, but this is what we're going to choose. So I'll choose x, y, and z at random. And that's not really at random because they have to satisfy this predicate. Okay, so it's not really at random. Okay, and you can check that if you look at the expectation of xi, yi, sorry, then you get minus 1/3. Okay, so if you choose xy random in the sense that for each I, xi, yi, zi is chosen among the 6 options, which are not all equal, then and you look at the correlation between 2 bits, then it will be exactly minus 1/3. Yeah, it's also the same as saying that you're applying noise with rate minus 1/3, but we can just be more concrete. Okay, and now we're almost done. See, like this and like this. Works. Okay, so if you now substitute this, okay, so what is the expectation of f of x, f of y? Okay, you need to do some short calculations that we're going to skip, but it's pretty easy using the orthogonality of Fourier characters, blah, blah, blah. And what we're going to get is the following thing. Okay, so this is what we're going to get. And we get the same if you take the expectation of any of the other terms. Okay, so if we multiply this by 3, then this is going to be equal to minus 1. So this is going to be equal to minus 1/3. Yeah, and we also said that the function f is odd. Okay, and the final thing I have to mention is that if you sum over all s, then you're going to get 1. This is the Parseval's identity. This is because of the normalization we use. Because on one side it's expectation, and on the other side it's the sum. Okay, and like I said, f is odd. Okay, now the question is, how can that be? So which functions f satisfy these conditions? So we see that the only way in which this is possible is if the only non-zero Fourier coefficients of f are of size 1. Okay, so the most negative that this thing can get is minus 1/3, and basically we have to put all the mass on sets of size 1. This is the only option. So the Fourier transform of f is concentrated, it's supported on sets of size 1, and this implies, again, we'll see a proof, but it's a very easy fact, that f is one of the following functions. It's either plus xi or minus xi for some I. Okay, now let's see, let's pause for a second. So what does this mean? So if f is a function xi, then it's like asking the ith voter, what do you think? Okay, so it's called a dictator, because xi dictates what happens. This is like the source of this terminology of dictators, which then gets used up in like extremal combinatorics also. And if f is minus xi, which we usually rule out by adding some axiom which rules it out, then we ask xi what they think, and then we do exactly the opposite. Okay, this is also allowed by the rules unless we somehow rule it out. Okay, so in conclusion, the only way to get a social choice function which always works is if we get Alex to decide what happens. Okay, so this is known as Arrow's impossibility theorem, Arrow's paradox, maybe there are other names. And this is something that we don't want, okay, because we believe in democracy.
Not anymore.
Yeah, we used to believe in democracy. Believe in democracy, and we definitely don't believe in dictatorships. Okay, maybe we can agree on that. So you can ask, okay, so maybe the problem is that I really insist that for any kind of vote, I'm always going to get a non-circular aggregated ranking. Yeah, so if I always insist that the ranking is an actual ranking, then yeah, you have to take a dictatorship. But what if I make this crazy assumption that the votes are completely random? And now it's okay for me if with probability 1% something goes wrong. And I then get something which is dramatically different from a dictatorship or its opposite. Yeah, this is the question that Kalai asked himself. Okay, so can we escape the paradox by allowing failure with probability epsilon? Okay, so if there is failure with probability epsilon, then what changes? So this equation, it's with probability epsilon is equal to 1, and probability of 1 minus epsilon is going to be equal to -1. Okay, so in this case, what I get is I sum over all s minus 1/3 is s f of s squared. This is going to be equal to -1 minus 2 epsilon over 3. Yeah, so it's almost equal to -3. Okay, don't worry too much about epsilon to epsilon. We don't care about constants. I know in this community a lot of people really care about constants. So I will care about constants in the exponents, but multiplicative constants, I couldn't care less. Okay, this is in TCS, we never care about multiplicative constants. Okay, so this too is correct, but really I don't care. So how can this happen? So now instead of f being supported on sets of size 1, now it's concentrated on sets of size 1. Okay, so this implies that the restriction of f to sets other than 1, okay, which is, this is a sum over all s, size different than 1, f of hat s squared, and this is order epsilon. Then, if I wanted to, I could compute this constant, but like I said, I don't care, so I didn't even bother in my lecture notes. Yeah, but you can compute it if you really care. So this big O just hides some constant. Okay. So in this case, the function f, it's not degree 1. So what this means is just close to degree 1. Okay, so it's instead of being supported on sets of size 1, now it's just concentrated on sets of size 1.
Are you sure you want it minus 2 epsilon, not plus 2 epsilon?
Okay. Yes. Thanks. Yeah. So now Friedgut Kalai and Asaf Naor, who is the brother of a famous basketball player.
Seriously?
Yeah.
Oh my god, I didn't know that they were related.
Matan Naor. So they asked, okay, so what can you say about the function f in this case? Okay, and they wrote a paper, and the guy found a mistake in the paper, and they corrected it. And this is what we're going to do in next. Okay, so Kn. What can you say about f? So you can see that this is a question that actually makes sense because it came from some other paper. So it actually has some application. Supposedly it's used in Dinot's proof of the PCP theorem. But I think these are the only applications I could find, which is better than zero. Yeah, so what we're going to do is we're going to start with the epsilon equals 0 case, which is quite easy. And then we're going to do the same proof and see what actually needs to be done. Okay? And we're also going to consider a slightly more general question, although, as Guy noticed, you can actually reduce between the two questions, which we won't bother doing. Okay, so warm up. So let's say that f minus 1, 1, n to minus 1, 1, and switch to capital F has degree 1. Okay, degree 1 just means that it's supported on Fourier coefficients of size at most 1. Okay? Okay, so what we do now is we're going to apply the Laplacian, which actually made an appearance already in non-stop, but we're going to define it again. So we're going to look at LIF, which is defined like this. So you take your function and then you flip the ith coordinate. And you take the difference and you divide by 2. And you do it because it's Fourier expansion looks like this. Well, I guess in this case it's just Ci xi. Okay, and you can also divide by xi, and it's going to make a difference. Okay, so the point here, because these two values are always plus or minus 1, and when you take the difference and you divide by 2, then you get 0 or plus minus 1. Okay, so this is always 0 or plus minus 1. And again, this is because if you take any two plus minus 1 elements and you take the difference and you divide by 2, you can check. You get 0 or plus minus 1. Okay, it's also used in norms talk when we compare norms of these things. Okay? So this means that this Ci is also in 0 plus minus 1. Okay, and we also know that C0 squared plus sum of ICI squared is equal to 1. Okay? This is again this Percival identity. So now there are two options. Either all of these are 0, or exactly 1 is not 0. Okay, there can't be two which are not 0 because then this would violate this equality. Okay? Okay, so either all Ci equal to 0, in which case f is constant, or a single Ci is equal to plus minus 1, in which case f is plus minus xi. Okay, these are the two options. Okay, it's not a difficult theorem. It gets a lot more difficult to do these things when you work over more interesting domains like the symmetric group. Then it's a lot more difficult. Or let's say the Graphman scheme. So these are some things that I might get into. So even these kind of factorization of Boolean degree 1 functions, it can get more complicated if you work over more complicated domains, but for now it's very easy. Okay, so this was the warm-up, and now let's try to do the same, but only under the assumption that f is close to degree 1. Okay, so now it's the SKN theorem. So now we're given f, which is from minus 1, 1 to the n to minus 1, 1, and f larger than 1 squared is most epsilon. This f larger than 1 is the sum over just a part of the Fourier expansion corresponding to set of size larger than 1. Okay, and so this is slightly more convenient to look at f, which is the low degree part of f. Which is the same thing that's within set of s more than 1, set of s not 1. And what we know about f is because small f is close to capital F, then this small f is close to minus 1, 1. Okay, so this satisfies that the expected distance between f of x and plus minus 1. Okay, so this is most the distance between f of x and capital F of x, okay, which is most epsilon. Okay, so we move from a Boolean function which is close to degree 1 to a degree 1 function which is close to Boolean. You can also go the other way if we wanted to. Okay, now we will try to just do the same proof and see where and if we get stuck, and then see if we can get unstuck. Okay, so you can do the same sort of game with this directional Laplacian. And what you will get is, you'll have to believe me, so we write again this time small f as this thing, so let's write this. F is C0 plus sum over I of Ci xi. And this time the C0 squared plus the sum of Ci squared. This is like 1 minus epsilon, right? And you can show that Ci, like this. So the distance between Ci and 0 plus minus 1 squared is order epsilon. I think it's you can value actually epsilon if the constant is 1, but let's not worry about it. Because we don't care about, I don't care about constants. And you can later on get the optimal constant using hyperconductivity anyway. So yeah, so the first step was fine. So you don't have to believe me, but you do the same sort of stuff, and this is the conclusion you will get to. Okay, so each of these CIs is individually close to 0 plus minus 1. Okay, and now again you have two cases. Okay, so case 1, in which all the ci's are close to 0. Okay, so ci squared is order epsilon for all I. Okay, in this case, we want to show that f is close to. Oh yeah, I didn't say the punchline, but the FPN theorem will state that the only one which is possible is if you close to either a constant function or a dictator. So there's no way to escape the paradox. Yeah, sorry, I forgot to say this punchline. So again, so in Arrow's theorem, if we're always successful, then we have to be a dictator. In this case, if you're just successful with probability 99%, then you're going to be 98% close to a dictator. Yeah, that's what's going to happen, so there's no way to escape the Arrow's impossibility theorem. Yeah. Anyway, so in this case, we want to show that f is close to a constant function. And case 2 will be that ci square, ci0 square is ci0 minus plus minus 1 squared is order epsilon, and ci squared is order epsilon for all I other than I0. So these are the only two cases, assuming epsilon is small, which we can assume. Okay, and in this case, we would like to show that f is, rather, we want to show that capital F close to a constant function, and here we want to show that capital F is close to plus minus x I0. Yeah, so in this case, the guess is that the function should be just essentially constant. The original function, capital F, which was the Boolean function. And if there is a strong Fourier coefficient, let's say ci0, then we should be close to a dictator on xi0. Okay, so that's what we're trying to do. And the thing is that this case reduces to this case. Okay, because essentially we're going to consider what happens when xi0 is equal to 1 and when xi0 is equal to minus 1. And for each of these settings, we kill this problematic Fourier coefficient. And then we use the argument of case 1 to conclude that for each of these substitutions, we get a constant. So in total, we get a function which depends on just the coordinate xi0. Okay, so we can reduce from this case to this case by just getting rid of xi0 by substitution. This doesn't work like this, I think, in higher degree, but at least here it does work like this. Okay, so it's really enough to prove case 1. Okay, and how are we going to prove case 1? So just a simplification, we're going to prove that little f is close to some constant function. Okay, and because little f is also close to plus minus 1, then this constant function has to essentially be plus minus 1. And then capital F is close to small f, so capital F will be close to plus minus 1. Yes, I'm not sure if you followed, but it's enough to show that, that small f is essentially constant. Okay, so it's enough to show that the variance of small f is order epsilon. Okay, and here I really care about this exponent. Like there's no reason to, but we can get the optimal exponent, which is 1, so we're going to try to get it. Okay. So now the reason I'm doing this proof in the first place, rather than just stating the theorem and saying, okay, you can prove this, is because I wanted to observe what's happening here. So what we got from the original argument, the simple argument, was that each of these Fourier coefficients on its own is small. But what we need to show that if you sum all of them, then it's still small. Okay, so when we proved Friedgut's junta theorem, we were able to do this by replacing this epsilon by some power of epsilon, okay, using hyperconductivity. The only proof I know of the FAN theorem involves some sort of induction. Okay, so there's the original proofs in the FAN paper, which are a bit mysterious. I never understood them. There's one proof, and then there's a second proof, which nobody ever looks at, using some result, which from some other people. Anyway, there's the proof in Guy's thesis, which is it does straight induction. It doesn't appeal to anything. And here we're going to attempt to give a proof using the Berry-Essen theorem, which I don't know how you usually prove it, but you could prove it by induction. So, in that sense, there's induction hiding there somewhere. Okay, and there's some hyperconductivity for degree 1 function. You can prove it just using some inequality, and you don't see the induction. It's just some summation. But anyway, yeah. So to recap, we have this function small f, okay, and we know that it's close to -1, 1. And we know that all of its individual Fourier coefficients are small. And we want to show that it's essentially constant. Okay? And the observation is that because these level 1 Fourier coefficients are small, and this is a linear function, then this is essentially a Gaussian. Okay, and so say this is -1 and this is 1, and we have this Gaussian, and it's always, let's say with constant probability, it's really close to these 2 points. Okay, and the only way in which this is possible is if essentially it looks like this. Yeah, there's no way that a Gaussian can somehow be high here and high here, but low here. It's impossible for a Gaussian. Okay, and there are many ways to argue it. Some of them are more mysterious, like this proof using hyperconductivity. I can never remember. Hyperconductivity. Yeah, there's some tricks and compute some moment. And anyway, you can ask Noam, but Noam understands it very well. So the intuition, but we're going to use the Berry-Essen theorem. Okay, so suppose is this. Then we define sigma squared is the sum of ci squared. And yeah. So the probability that, so this is for all t. So we're going to say that the distribution is close to Gaussian in CDF distance. Okay, so for all t, the probability that f is smaller than t is close to the probability that a Gaussian with the same mean invariance is close to most t. Okay, up to 1. So there's a constant, but I think the constant is less than 1, so we can just forget about it. So it's sigma to the -1 times the maximum for all I of expectation of ci xi cubed over the expectation of ci xi squared. Okay, there's an even stronger version, but this will be enough for us. Okay, so this is just some quantitative version of the central limit theorem. Okay, now in our case, the expected value of xi is 1. So this thing is the expected value of the absolute value of ci cubed. This is the absolute value of ci squared. So the ratio is the absolute value of ci. And this is a close square root epsilon. Okay, so this is order of square root of epsilon over sigma squared. Okay, again, so in our particular case, we can just forget about the xi's and we're comparing ci cubed to ci squared. Ci cubed over ci squared is ci is square root of 2. Okay? And we wanted to prove that sigma squared is bounded by epsilon. Okay, so if sigma squared is at most 1,000,000 epsilon, then we're done. Million is probably an exaggeration, but just to play it safe. Okay, so we assume that sigma squared is at least 1,000,000 epsilon, and then this thing here is small. Okay, so then the approximation is good. Okay, so now we're going back to this picture there. So we know that in expectation, f is close to 1 or minus 1. Okay, so applying Markov's inequality, we know that with constant probability, it's within some 10 squared epsilon of minus 1, 1. So let's say with probability 0.9. F is inside a minus 1 minus 10 squared epsilon, plus 10 squared epsilon, or 1 minus 10 squared epsilon, and plus 10 squared epsilon. Okay. Now, because sigma squared is so big, then we can apply this variation theorem, and the same will hold for the Gaussian. Okay, so let's say with probability 0.8, same holds for the Gaussian C0 sigma squared. Okay, and now we have a bound on the concentration of Gaussians. Okay, so this is something like squared epsilon over sigma standard deviation. So the probability that the Gaussian is found in this interval is the order of squared epsilon over. Okay, so the probability that the Gaussian lies in an interval of length, in this case it's 40 squared epsilon over sigma standard deviation. And the most order squared epsilon over sigma. Okay, but this is just because
It's a
bounded density.
The union of intervals.
Sure, yeah. Right.
So set.
Set. Right, so here we apply the variation theorem twice. Okay, so this thing should be at least 0.8. This should mean that the sigma squared is order epsilon. Yeah, I mean, this can only happen if you're very, very concentrated. Okay, this is maybe it's some calculation, but what it means is that there's this picture there. Okay, this is some way to carry this argument completely forward. Okay, so on the one hand, I'm very close to -1, 1, and on the other hand, I'm this Gaussian, so the Gaussian needs to be very small variance. Okay, it's not a complicated argument. Okay, so and this completes the proof of the FKN theorem. Lastly, I've never seen this proof anywhere, so.
Somehow, can you mention it? Even the second proof that you said in that paper, I mean, in reality, is not far from various, rather than talking about proximity distribution, proximity of second moments. So somehow similar, I guess.
Yeah. So I agree, and it just I feel like whenever you use hyperconductivity, you're using some trick, and here we're also using a trick. Here the trick is a variation theorem, but maybe it's more intuitive as a trick. I don't know. So yeah, in the end, all proofs are similar except for Guy's inductive proof, which is maybe a bit different. Okay, so this was the proof of the FKN theorem. So I'll pause for questions. Meanwhile, I'll erase the rest of the board. Okay, any questions while I was erasing the board? If you have 15 minutes for a question, then we have to fill them. Get ready with your trick questions. This FKN theorem has also some version for LP. I don't remember what kind of version makes sense and is different from this, but at the time at least I thought that there was one. And probably this proof works, but definitely if you use Guy's inductive proof, then it will give you the LP version. You just need to change 2 to be in a few places. And the issue there is to get the correct dependence on the constant, like this. There is this constant here, and you want to get the right constant, the right dependence on P. You can also look at infinity versions where there's like a threshold phenomenon. Anyway, yeah. So where do we go from here? So we can go from here in at least 2 different directions. Okay. So where do we go from here? Okay, so direction 1 is higher degree. Okay, so this was about functions which are exactly or close to degree 1 in the setting of Hitchin-Kahan, like we heard from Christoph. But in some cases, we are interested in degree D. Okay, so there's one standard example. So from spectral proofs of T intersecting Ehrlich-Kohaler theorem, whatever that is, then you get degree T. In the past few years, this kind of approach to Ehrlich-Kohaler theorem is kind of lost steam, because now we know that the right approach is using the normal junta method. But anyway, it still gives some motivation for understanding the degree T case, D case. There's this theory of complexity measures of Boolean functions, which relates degree to other measures. So we don't have a list of Boolean degree D functions, but we have some sort of characterizations, like they can be computed by Schiller decision trees. There's an approximate version, like an analog of the FKN theorem to degree D, approved by Guy in his thesis, and in the unpublished paper with Mustafa. 2 different versions of the 2 authors' websites. And since there are many different proofs. I know people like Muli Safa are interested in what happens when the degree is large, like log n maybe, and then it looks very different. Anyway, this is the direction we might go to later, but not right now. Right now we're going to finish soon, but tomorrow. The other thing you can consider is the different domains. You can also consider different range, but we don't do it so much. There's like one paper. Okay, what do I mean by different domains? So now my function either it just doesn't live on -1 to the end, like maybe it lives on some of the groups that Noam was discussing, or my favorite group is the symmetric group. Everybody and whatever they think. Maybe it's not even a group, it could be some association scheme, whatever that is. Okay, but even simpler, we can still think of the Boolean cube just with a different measure. Okay, so an example of domain is, so when we talk about skewed measure, we usually switch to 0, 1, and I've seen at least one paper which doesn't do that, but usually 0, 1. So it will be 0, 1 to the n, it's actually the mu p measure. Okay, what is this mu p measure? So mu p of a vector x is p to the sum xi, 1 minus p to the sum 1 minus fi. Okay, where p is between 0 and 1. Or if you identify 0, 1 to the n with the power set of n, like all the subsets, then mu p corresponds to the experiment where we choose each element and put it inside with probability p. Now, why do we care about this kind of domain? So when p is equal to 1/2 is essentially what we were considering. But in many cases, we care about what happens for other p. And the most interesting cases are when p goes down to 0. Okay, but even for constant p. So two examples. One example is in extremal graph theory, like the established coordinate theorems, whatever that is. We're interested in what happens. So typically they're for in uniform set systems, but it's a lot cleaner if you look at these kind of versions. And the other example, which hopefully everybody will be familiar with, is random graphs. Okay, so in a GNP random graph, hopefully everybody heard about it at least 10 times. So n is n choose 2, and we put in each edge with probability p. And typically p is going to be very small, like threshold for triangles is like 1/n. Okay, and then we saw Friedgut some version of Friedgut's junta theorem in non-stocks, and when p is small, then something else happens, and we have all these sharp threshold theorems. Okay, which is a different phenomenon. It's a phenomenon which happens when p is small. Okay, so what we're going to do tomorrow is we're going to see what happens for the LKN theorem when p is a different constant or going to 0. Okay? So the spoiler, when p is constant, it will be the same. You just repeat the same proof and it just works. But okay, I can say it now. So kind of what happens is instead of the xi, you need to work with a different basis, which is orthogonal with respect to the p-biased inner product. So when you're finding the inner product, you take an expectation with respect to mu p, and you have a different basis. And as p goes to 0, the third moment of this basis elements is going to blow up. And this is why this is going to stop working. Okay, so for constant p, everything works. Like you need to change the beginning, but everything works. And it gets a lot more exciting when p is small. Now, when p is small, I mean p goes to 0 with n.
You mean p is small with respect to n?
Yeah. And then we have, I know of two approaches of handling p small. One is due to Noam, global hyperconductivity. Noam, are you going to discuss it?
Probably not.
Yeah, that's too bad. Yeah, I'm also probably not going to discuss it, but it's a pity because it's the major thing which has been happening in this area in the past decade. Okay, so this is one approach. So we haven't seen hyperconductivity, but this is this induction which is hidden inside all the proofs in Boolean function analysis, and this fails when p is small for similar reasons like this. but you can rescue it, so it works for pseudo-random functions. What Noam calls global functions. So this is one approach, and we're going to see a different approach. So I won't tell you the approach because, well, it's going to be a reduction to the case people have. That's what we're going to see, hopefully, tomorrow. So I took away some of your question time, but if you still have questions, like we already had one from Alexandros.
Well, let's thank Yuval first.